Hi guys, it's Dr. Justin Souther here, going through some of the tutorial questions which will hopefully help you get started on this week's assignment. In this question we asked to show that the following function is a solution of the wave equation. In other words, we want to show that this function satisfies the relationship where the second partial derivative with respect to t is equal to some constant times the second partial derivative with respect to x. Okay, so the first step, of course, is going to be to work out these partial derivatives. Before we can work out the second partial derivative, we need to work out the first partial derivative. So let's first do it with respect to x. So we're differentiating u with respect to x. That means we treat t as a constant. Well, this is just equal to, here we've got some function of x to the power of 6. So the chain rule, the outer function, bring down the 6, keep the inner function untouched, decrease the power by 1, and multiply by the derivative of the inner function. Well, the derivative of the inner function gives us derivative of x with respect to x gives us 1. The derivative of minus at with respect to x gives us 0. So the derivative of the inner function is simply 1. We multiply by 1. We can leave that off. Plus, do the same thing here. Differentiate the outer function, leaving the inner function untouched. Multiplied by the derivative of the inner function, which once again is 1. Okay, so we found the first partial derivative with respect to x. We now want to find the second partial derivative. In other words, we're just going to differentiate again with respect to x. And that's equal to, once again, chain rule. Bring down the 5. You get 30 x minus at all to the power of 4. Again, multiplied by the derivative of the inner function, which is just 1. Plus 30x plus at to the power of 4. Multiplied once again by 1. Right, so we have found the second partial derivative with respect to x. Let's do the same for t. U subscript t is now going to be equal to, once again, same thing, 6x minus at, keep the inner function untouched, multiplied by the derivative of the inner function. Okay, here it's not just 1. The derivative of x with respect to t, we treated x as a constant, that's 0, but the derivative of minus at with respect to t is, of course, minus a. And then we're going to add the derivative of this with respect to t, and that's 6x plus at to the power of 5, multiplied by the derivative of the inner function, which in this case is 0 plus a. Okay, now we need to find the second partial derivative with respect to t, so we just differentiate this guy again. Now note that this negative a is just a constant. We could have taken it to the front, but I'm going to save time, not write it all out again. The actual function that we have to differentiate is this guy here. The constants just stay. Bring down the 5, we get 30 x minus at all to the 4, multiplied by the derivative of the inner function, which is minus a. We've already got a minus a. We're going to multiply those two together to get a squared, positive a squared, plus the derivative of this guy with respect to t. That once again is going to be 30, bringing down the 5, x plus at all to the 4, multiplied by the derivative of the inner function, which once again is a. We've already got a as a factor there, so we need to have a times a is a squared. Alright, we're almost there. We're now just going to factorize out this a squared over here, which leaves us with 30x minus at to the 4 plus 30x plus at to the 4. Oops, that should have been 30. And now if you look at this, you'll see that this thing here in the bracket is exactly the same as this over here. In other words, this is equal to a squared times the second derivative, partial derivative with respect to x, which is exactly what we were trying to show. Here, the second partial derivative with respect to t is equal to a squared times the second partial derivative with respect to x.